Hello everyone, myself Akash, founder and director of Prime Stock Mathematics Amravati. In today's video, we will solve an interesting question on group theory from CMI MSc PhD Entrance 2022 exam. Question is, pick the correct statements from below. We have given 4 different statements and we have to determine which of these given statements are true, that is correct. So let us verify one by one each of these statements. Statement A is no group of order 625 is simple. Is this a true statement? Yes, it is a true statement. To see it, we will use the result. A finite P group cannot be a simple unless it has order P where P is a prime. Okay. What is P group? A group is said to be a P group if its order is some prime power. Okay. So according to this result, a finite P group. So that is, this result states that if order of G is P to the power n, unless it has order P. So if order of G equal to the P to the power n, where n greater than 1, then it cannot be a simple. Then G is not a simple group. Okay. What will happen if n equals to 1? If n equals to 1, then it has order P. And we know that a group of prime order are cyclic group and they are isomorphic to ZP. And we know that the group ZP has no proper normal subgroup. So they are simple group. So when n equals to 1, then order of G equals to P and the group will become simple. But when n greater than 1, then according to this result, G is not a simple group. Okay. You can easily prove this result by using class equation of group. Okay. So what is the statement A? No group of order 625 is simple. So we have given order of G equals to 625, which is equals to 5 to the power 4. Clearly, it is of the form P to the power n, where n greater than 1. So according to this result, we have G is not a simple group. That is, if order of G is 625, then G is not a simple group. So no group of order 625 is simple. So this is a true statement. So we mark it as correct. Now let us move to the statement B. Now the statement in B is GL2 over R is simple. What is GL2 over R? Group of all 2 cross 2 invertible matrices over real numbers. Is it a simple group? No. It is not a simple group because it has a proper normal subgroup. We know that a group G is a simple if it has no proper normal subgroup. But this group has a proper normal subgroup, and which is SL2 over R. SL2 over R is a normal subgroup of GL2 over R. You can easily prove it. To see it, consider B belongs to GL2 over R and A belongs to SL2 over R. Okay. As it is a group and it is a group of all invertible matrices. So B belongs to GL2 over R implies B inverse also belongs to GL2 over R. Now consider determinant of BA B inverse. We know by properties of determinant that determinant of BA B inverse can be written as determinant of B times determinant of A times determinant of B inverse. Okay. And this can be written as determinant of B times determinant of A times 1 over determinant of B. Since B inverse exists, so it is an invertible matrix. So its determinant is non-zero number. So it is well defined. So this will get cancelled out and we remain with determinant of A. As A belongs to SL2 or R, and we know that SL2 or R is a group of all invertible matrices whose determinant equals to 1. So A belongs to SL2 or R implies determinant of A is equals to 1. Okay. So we see that determinant of B inverse is equals to 1. So it is also an invertible matrix and its determinant is 1. So this implies B inverse belongs to SL2 over R. And since B and A are arbitrary, so this holds for every B belongs to GL2 over R and A belongs to SL2 over R. So, by definition of normal subgroup, we see that this implies SL2 over R is a normal subgroup of GL2 over R. Okay. And so we see that GL2 over R has a proper normal subgroup, which is SL2 over R. So it cannot be a simple group. So this statement is incorrect, that is false. So we will discard it. Okay. Now let us move to the third statement. Statement C is let G be a simple group of order 60, then G has exactly 6 subgroups of order 5. Is this a true statement? Yes, this is a true statement. To prove it, we will use Sylow theorems. Due to the length of the video, I will not write the statements of Sylow theorem here. To see the statements of Sylow theorem, you can check out the description of this video. Now, we have given that G has order 60, which can be written as 2 square times 3 into 5. Okay, and it is also given that G is a simple group. Okay, G is a simple group implies G has no proper normal subgroup. Okay, by definition of simple group. Okay, now by Sylow first theorem, we know that if P to the power n divides order of G, then G has at least one subgroup of order P to the power n. Okay. If P to the power n divides order of G, then G has at least one subgroup of order P to the power n. Here, 2 square divides 60. So, G has at least one subgroup of order 2 square. That is, G has Sylow 2 subgroup of order 4. Similarly, G has Sylow 3 subgroup of order 3. G has Sylow 5 subgroup of order 5. Okay. So, as we are only interested in subgroups of order 5, so I write only for the case 5. Okay. So, G has Sylow 5 subgroup of order 5. This is by Sylow first theorem. Okay. By Sylow first theorem. Now, if I denote N5 equals to number of Sylow 5 subgroups, because Sylow first theorem only state that if P to the power n divides order of G, then G has at least one subgroup of order P to the power n. G may have more than one subgroup of order P to the power n. So, let us denote the number of Sylow 5 subgroups by N5. Then by Sylow third theorem, we have N5 congruent to 1 mod 5. Okay, and N5 divides 2 square into 3, that is 12. This is by Sylow third theorem. And only possibilities for N5 are N5 equals to 1 or equals to 6. You can verify. For example, when N5 equals to 1, then 1 congruent to 1 mod 5, because 5 divides 1 minus 1, that is 0. Okay, and n5 when equals to 6, then clearly 6 congruent to 1 mod 5. Okay, because 5 divides 6 minus 1. Okay, so also when n5 equals to 1, 1 divides 12, and when n5 equals to 6, 6 divides 12. So these two numbers satisfies these two conditions. And if n5 other than these numbers, for example n5 equals to say n5 equals to say 11, okay, then clearly we can see that though 11 congruent to 1 mod 5, because 5 divides 11 minus 1, but 11 does not divide 12. Okay, so n5 cannot be equals to 11. Okay, so only possibilities for n5 are 1 or 6. Now it is given that G is a simple group, so G has no proper normal subgroup, and hence we must have n5 not equals to 1, because we know by corollary that a Sylow P subgroup is a normal if and only if it is unique. Okay, so Sylow 5 subgroup is a normal if and only if it is unique. So when n5 equals to 1, Sylow 5 subgroup will become normal subgroup. But G is a simple group, so it has no proper normal subgroup. So n5 cannot be equals to 1. Okay, since otherwise it will be normal. Okay, so only possibility remain is n5 equals to 6. Okay, so number of Sylow 5 subgroups of G is 6. So G has exactly 6 subgroups of order 5, because each Sylow 5 subgroup has order 5. So G has exactly 6 subgroups of order 5. So the statement in C is a true statement, that is correct statement. So we mark it as correct. Now let's move to the statement in D. The statement in D is, let G be a group of order 60, then G has exactly 7 subgroups of order 3. Note that here it is not given that G is a simple group like it is when it is given in C. Here it is only given that let G be a group of order 60, then G has exactly 7 subgroups of order 3. Is it a true statement? No, it is not a true statement. To see it, given that order of G equals to 60, which can be written as 2 square times 3 into 5. Okay, so by Sylow first theorem, as we have seen in a case of statement C, by Sylow first theorem, G has at least one Sylow 3 subgroup of order 3. This implies G has at least one Sylow 3 subgroup of order 3. This is by Sylow first theorem. Okay, and by Sylow third theorem, if n3 denotes number of Sylow 3 subgroups, then by Sylow third theorem we have n3 congruent to 1 mod 3. Okay, and n3 divides 2 square times 5, that is n3 divides 20. This is by Sylow third theorem. So only possibilities for n3 are clearly 1 congruent to 1 mod 3 and 1 divides 20. So possibility is 1. Okay, comma 4 congruent to 1 mod 3, because 3 divides 4 minus 1 and 4 divides 20 as well. So other possibility is 4. Okay, and 10 congruent to 1 mod 3. Okay, because 3 divides 10 minus 1 and 10 divides 20 as well. So another possibility is 10, and you can verify that there are no other possibilities. For example, if we say another number which divides, which is greater than 10 and which divides 20 is 20 itself. But 20 does not congruent to 1 mod 3 because 3 does not divide 20 minus 1. So these are only possibilities for N3. And so number of Sylow 3 subgroup can be equals to 1, number of Sylow 3 subgroup can be equals to 4, and number of Sylow 3 subgroups can be equals to 10. Okay, so the statement in D states that G has exactly 7 subgroups of order 3. No, because N3 can be equals to 1, 4 or 10. And order of N3, G has exactly one Sylow 3 subgroup of order 3. And order of N3 is 3. So G has either one subgroup of order 3 or 4 subgroup of order 3 or 10 subgroups of order 3. But G never has 7 subgroups of order 3. So the statement in D is incorrect, that is wrong. So we mark it as cross. So the correct answer to this question is option A and option C. That is, statement in A is true statement, statement in C is true statement. Okay. So if you found this video interesting and helpful, then please like and share this video and subscribe to our YouTube channel. Thank you for watching.